Welcome to Teledyne CETAC Technologies webinar, Detection of Uranium in a Very Hard Water Matrix Using Ultrasonic Nebulization with ICP-AES Detection. I'm your host, Bob Armbruster. Today our Nebulizer Product Manager, Fred Smith, will be giving a presentation covering the different aspects and capabilities of the Ultrasonic Nebulizer. Please save any questions to the end of the presentation, at which time Fred will field any that you may have. Just a note that the webinar will be available for download on our website in the next few days. On that note, let's get started. Fred, please start your presentation.
Thank you very much for the introduction, Bob. This webinar is covering a particular application that came our way, and that's the detection of uranium in a very hard water matrix using ICP-AES detection. Uranium is a regulated element in drinking water around the world, and per the USEPA guideline, the MCL, or the maximum contaminant level, is 30 micrograms per liter. Uranium in groundwater can occur from natural leaching of mineral deposits, and it came to our attention that subsequent very hard water matrices from this natural leaching are present in areas such as southeastern UK and southern Germany. So this presentation will examine the utility of coupling an enhanced nebulizer system, that being an ultrasonic nebulizer, with ICP-AES for improved detection of uranium in a simulated very hard water matrix. Now, there are two primary human health concerns for uranium. The main one is that uranium is a heavy metal and can cause impaired kidney function, also called nephritis. There's also the issue of uranium being a radionuclide. For example, U-238, the main isotope of uranium, is an alpha emitter. Sources of uranium in the environment, again, include the leaching from mineral deposits, mining of uranium, burning of coal, emissions from nuclear power plants, munitions, for example, depleted uranium that is used in these munitions, and phosphate fertilizers because of the affinity for uranium to combine with phosphate. Hard water can occur from the dissolved solids content from groundwater upon exposure of mineral deposits to things such as calcium and magnesium carbonates. The designation hard water describes water that is hard to use with soap. So when you combine the soap with the water, you get less formation of soap lather. There are various units used around the world to describe the extent of water hardness, and these include degrees of general hardness, grains per gallon, German degrees, English degrees or degrees Clark, French degrees, and parts per million. Parts per million specifically meaning milligrams per liter, as calcium carbonate also sometimes combined with magnesium carbonate. For definition of units, we'll note the degrees of water hardness in this scale from the U.S. Geological Survey: soft, moderately hard, hard, and very hard. And we will look at an example of water from a municipal water source and compare it to the USGS scale. And there's a web link there at the bottom of the slide that you can click on and look for more information about water hardness. So first, we'll look at a number of maps. And again, these are general maps. This is just a UK map with a source from Wikipedia. But this is sort of describing in general the water hardness that is observed in the UK, and drawing a line from Newcastle in the northeast down to Exeter in the southwest. To the right of that line, of the blue line, or the southeastern part of the UK, is generally where there is harder water. At the bottom of the slide, there is a link for a detailed UK hard water map. With that, we also looked at areas in the UK where there can be higher levels of uranium in the groundwater. There is, again, with the reference at the bottom from the British Geological Survey, a very detailed UK uranium and water map. We'll just point out a couple of areas in the UK where uranium levels are higher, that being in the West Midlands region, closer to the Wales border, and the Central Lowlands, also called the Midland Valley in Scotland. The other area that came to our attention was the prevalence of hard water in Germany. This is a German map from Free Vector Maps. In particular, the areas where harder water is observed in the northeast, in the German state of Mecklenburg-Vorpommern, and in the south, Baden-Württemberg and in Bayern. Slide, there's a link for a detailed hard water map of Germany if you go to that link. Uranium and water in Germany, there again is a detailed reference for that from 2012, uranium in German tap and groundwater in the book Occurrence and Origins in the New Uranium Mining Boom. The higher levels that are seen naturally are in sort of the Middle Eastern German states of Thüringen and Sachsen. In the United States, and there on the middle of the map, I marked where the CETAC factory is. In the central United States, there is Omaha on the border between the states of Nebraska and Iowa. You can see there is a prevalence of hard water, particularly in the western mountain states and down into the southwest. Again, there is a detailed hard water map of the United States, and the link there is to the U.S. Geological Survey. What is of interest is, on the next slide, is the prevalence of uranium in groundwaters and the correlation of that in the U.S. with areas of hard water. In particular, two aquifers. One very large one called the High Plains Aquifer that includes 8 states in the central United States and the western states, and also the Central Valley Aquifer in California. There's a detailed uranium and groundwater map and a very recent reference from Environmental Science Technology Letters. I did put in the title of this. It says Natural Uranium Contamination in Major U.S. Aquifers Linked to Nitrate. That paper, and I won't get into the specifics then, links the prevalence of nitrate, particularly from fertilizers, and how the presence of the nitrate can increase uranium mobility in waters. So selected drinking water standards for uranium around the world. The World Health Organization, or the WHO, has a current limit of 30 parts per billion, as the US EPA. Other countries are lower, such as Australia and Canada, but in particular Germany. And Germany's uranium limit in drinking water is 10 part per billion. And that was one of the reasons for looking at uranium at this level in a very hard water matrix. There is a provisional WHO limit of 15 micrograms per liter of uranium. The limit now is based on the consumption of 2 liters of water per day and an average human weight of 60 kilograms. There is an additional German standard which is even lower, and that is only 2 part per billion, and that's used for water used for the preparation of baby food, obviously because of the smaller mass of the baby in comparison to an adult. So the equipment that we used in this study included both an ICP-AES and an ICP-MS and an ultrasonic nebulizer. The ICP emission instrument that was available was the PerkinElmer 5300 DV system. And for an ICPMS experiment, we had the Thermo Fisher ICAP-Q available. The ultrasonic nebulizer is the Teledyne CETAC U5000 AT+. So, general in general, instrument detection limits for uranium are about 1 to 10 micrograms per liter or 1 to 10 part per billion for ICP-AES. ICP-MS is much lower, down to around 0.1 part per trillion. If one needed to go lower for ICP-AES, one way was the possible need for pre-concentration of uranium by chelation, or you may have to look at an enhanced nebulizer system, such as an ultrasonic nebulizer, to try to reach lower levels. So on the ICP emission system that we're going to use, the Perkin-Elmer system, there are 5 available uranium wavelengths, and I have listed them here in decreasing intensity. So these are the wavelengths we were initially going to look at in this very hard water matrix after spiking it with uranium. So first, here is a front view of the U5000 AT+, the ultrasonic nebulizer from CETAC. You can see in the glass chamber on sort of the middle left part of the unit the aerosol that's generated. And that's simply generated by pushing in the yellow operate button on the front of the unit. The principle of operation of the ultrasonic nebulizer is different from that of a conventional pneumatic nebulizer. In place of that conventional pneumatic nebulizer, we're using a piezoelectric transducer or an oscillating crystal to break up a flowing liquid into an aerosol. The ultrasonic nebulizer is typically 10 to 15% efficient for conversion of the liquid sample into a usable aerosol. Because of that higher efficiency, we do have to have an inline desolvation system to prevent plasma overloading with water vapor and maintain ICP stability. An important point is that the ICP-AES or ICPMS nebulizer gas is now acting as a pure carrier gas, simply moving the generated aerosol to the plasma. So in the ultrasonic nebulizer experiment, the generation of the aerosol is independent of the gas flow. Here is a general schematic of an ultrasonic nebulizer. There you see on the left the transducer assembly and the small chamber where the aerosol is generated. After that, the argon in simply comes in and carries the generated aerosol toward the ICP. But we have a heated U-tube first in place to maintain it as a vapor, then a condenser to remove any excess water, and then the dried aerosol particles will come out of the condenser and go into the ICP. Here is a close-up view of the transducer, and what I'll point out is there is a piezoelectric disc denoted by the orange arrow. On top of that is placed a quartz faceplate, and the liquid sample will move or be pumped across that quartz faceplate. The vibrations are coupled from the piezoelectric through the quartz, and the aerosol is generated. An inside view of the USN then shows that heated J-tube, which in the schematic was in red. That's wrapped with a heating cord to keep the sample in a vaporized form. And then the condenser. The condenser is an electrothermal or Peltier-cooled condenser. It does not use a recirculating liquid or coolant flow to cool the condenser. So with the use of that electrothermal condenser, the size of the unit is quite compact. And you see there the placement of the ultrasonic nebulizer on the bench next to the ICP emission system we're using to give you some idea of the scale of the USN, meaning that it can be easily placed on a bench top or on a laboratory cart. Some operating conditions I would like to point out when using the ultrasonic nebulizer. This slide shows the normal conditions with a standard pneumatic nebulizer, in this case a glass concentric nebulizer. The nebulizer gas is probably the main parameter to adjust, and we're using a nominal flow of 0.62 liters per minute. Integration time in this experiment is 20 seconds with 3 replicates. We are using a standard size alumina torch injector at 2 millimeters ID. Operating conditions for the USN, there is a slight change in the torch position to the -4 position on the Optimus system for a drier plasma because of the condenser in line. But the main thing we adjusted was the nebulizer gas flow, and that was reduced to 0.52 liters per minute for best signal. So some specifics on the setup. The main thing we have to do is to remove the standard nebulizer and spray chamber from the back of the torch on the host ICP. And there are two things then to use. There is a nebulizer gas line that comes in a interface kit and a sample outline with a torch adapter. The torch adapter is the small white fitting that's attached to the back of the torch in the picture. In the experiment, we will use the host ICP-AES peristaltic pump. And you see the USN is now in a laboratory cart moved off the bench, so it's in close proximity to that. Of course, samples, you can connect the sample uptake line to an auto sampler if you wish, or if you have a limited number of samples, you can run them manually. Here is a back view of the ultrasonic nebulizer, which shows a little bit more detail of the two lines. You see the sample outline that's coming out the back of the unit that attaches to the ICP torch, and there again is the nebulizer gas line. One thing that I will point out is there is a fitting that snaps into the back of the ultrasonic nebulizer, and of course that carries the gas from the host ICP-AES. Normally we can set liters per minute in argon gas flow if the ICP is equipped with a mass flow controller. If not, if the ICP is only equipped with a pressure regulator, that fitting can be equipped with a flow restrictor to take the place of the concentric nebulizer. Finally, you see at the bottom of the screen with the red arrow, there is a drain pump, and that's to remove any condensed liquid out of the ultrasonic. Okay, so the recipe that was suggested for us to use for the very hard water matrix was quite fortified. 500 ppm or milligrams per liter in calcium, and 200 ppm or milligrams per liter each in magnesium, sodium, potassium, and iron. And these were all made from single element 10,000 ppm ICP grade standards. So this entire mixture then will compose our very hard water matrix. First, as a comparison, we did run a tap water matrix, and this was from a municipal water source here at the CETAC factory in Omaha, Nebraska. And we ran this on the same ICP emission instrument using the standard nebulizer and spray chamber to see what the concentrations were of some of the majors, that being sodium, potassium, calcium, and magnesium. The calcium level was measured at around 50 ppm or 49.3, and upon conversion to calcium carbonate, that gave us a calcium carbonate concentration of about 125 milligrams per liter. This, and if you coupled it with the magnesium carbonate, would classify this tap water more as a hard water sample. Not a very hard water sample, but as hard water. We then took this same tap water and we spiked it with a known amount of uranium, and were able to do a quick measurement using the thermal ICAP Q ICPMS, and came up with an approximate uranium concentration in the tap water of around 4 parts per billion. So just to give a visual idea of what some of these water samples can look like, we arranged a number of beakers and evaporated some water samples. Of course, deionized water, the beaker is clear. On the upper right, you see in the Omaha tap water some of the residue left behind. We had some extra estuarine water from the St. Lawrence Seaway. That's about 1% dissolved solids, so quite a bit more. And then the very hard water matrix we evaporated down, and of course you see the orange color from the iron that's in this simulated matrix. So experimental details, we prepared a matrix blank and 4 calibration standards, which were matrix matched for the very hard water matrix. And for the standards, we used 20, 50, 100, and 200 part per billion of a multi-element standard, including uranium. For this experiment, we used no internal standard. We wanted to see just what type of data quality we would get under these conditions with a very hard water matrix. So these solutions were introduced both to the standard concentric nebulizer and to the ultrasonic nebulizer, the U5000 AT+, using the onboard peristaltic pump of the host ICP. Instrument detection limits, or IDLs, were defined as 3 times the standard deviation of the matrix blank concentration. And that, again, is the very hard water matrix. Limits of quantitation, or LOQs, were 10 times the standard deviation of that matrix blank concentration. And we read back one of the middle standards, that being the 100 ppb standard, to measure percent recoveries. Here is a list of the MCLs, or again, the maximum contaminant levels, for some of the US EPA regulated elements. And there at the bottom you see uranium again at 30 micrograms per liter. But we'll look at these elements using both the standard nebulizer and the ultrasonic nebulizer in this very hard water matrix. So first, again, looking in order of the uranium wavelengths that are available, first we looked at the 385 nanometer wavelength. And we did notice, after parsing through single element standards of iron and calcium, some interference there at 385. Of note, we didn't really notice that much signal from the 200 ppb uranium standard. We then looked at the next wavelength in intensity, uranium 367, and we did notice a very distinct iron interference at that wavelength. There we did see measurable uranium at 200 ppb. So the next course was, well, could we generate any inter-element correction factors to use the most sensitive wavelengths at 385 and 367 to measure the uranium? And we got mixed results. We couldn't really get consistent readbacks of the standards that we had prepared. So the next was to attempt to use one or more of the less sensitive uranium emission lines with the hope that we could enhance the signal with ultrasonic nebulization. So the next wavelength we tried, the 393, well, that didn't work out very well. The signal was saturated, and of course, we then saw that the probable issue is the calcium interference. There is a calcium line, a very strong one, at 393.366, very close to that uranium line, which is swamping out any signal. So then we were down to 2 that were available. And the next one was the uranium 409 line. And here we were able to see an increase in the uranium signal upon introducing the 20, 50, 100, and 200 part per billion uranium standard. We then looked at the uranium 424 wavelength. And again, we were successful putting in the 20, 50, 100, and 200 part per billion uranium standard. Again, all in very hard water. We were able to see the uranium signal increase. So one of the things we first wanted to do was to compare the ICP emission intensity in this matrix for one of the standards. And we chose the 100 ppb standard, comparing the signal from the standard nebulizer, that being a glass concentric nebulizer, and the ultrasonic nebulizer, and looking at the factor. And certainly when comparing this, you can see a distinct improvement, depending upon the element, in a range of about a factor of 4.5 to 9 across these regulated elements. Particularly though for the uranium lines, the weaker lines, we did see a very marked improvement in signal when using the ultrasonic nebulizer. Next, looking at the calibration at the uranium-409 line, we ran again the 20, 50, 100, and 200 part per billion standards, and again we got very nice calibration of 4 nines for uranium-409, and then the same excellent correlation coefficient of 4 nines calibration using the 424 wavelength. So now we wanted to get an idea of the comparison of both the instrument detection limits and the limits of quantitation that we could achieve. So going back to the standard concentric nebulizer, we ran these same solutions through and came up with an IDL of a little bit under 10 part per billion for the uranium-424 wavelength. We tried the uranium-409, couldn't quite get a good calibration, so settled on the 424. And LOQ, though, is up near the 30 part per billion MCL limit from the US EPA. Recoveries across all of these elements were very good. Then performing the analogous experiment with the ultrasonic nebulizer, then we see the IDLs and LOQs, particularly for now both uranium lines. With the additional signal, we could calibrate the 409 line very well. We have IDLs around 1 part per billion with LOQs around 3 to 4 part per billion. Okay, well below the MCL from the US EPA and below the German limit of 10 part per billion. So comparing the two, and this is a comparison of the limits of quantitation. On the far right column is a factor. You can see for uranium, it's about a factor of 8 improvement in lowering the limits of quantitation. Now again, these will vary from element to element depending upon the signal that we can get from the element and the background noise from the very hard water matrix. Some things aren't improved as much, such as like selenium and chromium and lead, but the LOQs, again, are quite good, particularly with regards to this matrix. So we wanted to go one step further, and that was to try to calibrate a little bit further down, and that's closer to the limit in Germany of 10 part per billion. And in this case, we ran the experiment again, this with the ultrasonic nebulizer at 10, 20, 50, and 100 part per billion. The calibration is not quite as good. It's 0.9988. That's at the 409 line. A little bit better, 0.9992 at the 424 nanometer emission line. Again, 10, 20, 50, and 100 part per billion uranium. So then we ran the very hard water matrix back again as a sample. And the IDLs and LOQs again then are similar to that from the previous calibration using standards from 20 up to 200 part per billion. We're getting LOQs of around 4 to 5 part per billion. Recoveries, we were right on for the 409 nanometer line, a little bit high for the 424 line at 120, but still not too bad. So in summary, ICP emission with ultrasonic nebulization can detect down to 10 part per billion uranium in a very hard water matrix. The uranium emission lines are chosen carefully to avoid interferences from calcium and iron, particularly the most sensitive lines at 385 and 367 we could not use, so we had to use some of the weaker lines at 409 and 424. But the ultrasonic nebulizer provided us the extra sensitivity to measure those less intense lines. So with that, I'll open up the webinar to any questions any of the attendees may have. Okay.
Is it popping up on your screen? Question?
Let's see.
First one is
there a link to download
Nope.
the slides?
Are there certain elements that don't work well with an ultrasonic nebulizer, like boron?
Yes, boron is a problematic element. It tends to condense out in the condenser of the USN and be lost. You can add a matrix modifier, that being something like mannitol, to bind the boron so it will go through the ultrasonic nebulizer. There is a technical note on the CETAC website that you can access, and we did that study using both mannitol and tartaric acid. So you can do boron if your method can allow a matrix modifier.
Another question is, how does an ultrasonic nebulizer differ from a system like an Eridis?
Well, the Eridis system actually uses a conventional pneumatic nebulizer vis-a-vis the piezoelectric crystal of the ultrasonic. The desolvation, again, between the two is also different. With the ultrasonic, we're using an electrothermally cooled condenser. In the Eridis, we're using a membrane dissolvator to remove the water vapor.
Okay.
Any other questions that come up?
Just waiting to see if anybody has any other questions.
Yeah. And again, other things I'll point out about the Eridis 2 versus the ultrasonic. The Eridis is typically self-aspirated and uses a lower flow, anywhere from 50 to 200 microliters per minute. The ultrasonic nebulizer, you do have to pump the sample to the transducer. It can't be self-aspirated.
Okay. Does this mean that the ultrasonic nebulizer eliminates the problem of total dissolved solid content, TDS?
No, the ultrasonic nebulizer will not remove non-volatile inorganic solids. In fact, it will actually send more of it into the ICP. So with that in mind, you have to be wary of the dissolved solids content. In general, we recommend between 0.1 and 0.5% total dissolved solids. Above that, of course, you can overload the ICP, and in the case of ICP emission, you can suffer very large signal suppression. And in the case of ICPMS, you can have salting of the interface cones. So the solid matrix, like the salt, is not removed. In order to do that, you'd have to move to a sample preparation technique like chelation in order to chelate the elements of interest and remove things that you don't want, like sodium, potassium, calcium, and magnesium.
Okay. Are there any plans to, okay, let's see here. If coupled with an ICPMS, what sort of oxide ratio could you expect with an ultrasonic nebulizer?
Cerium oxide to cerium?
Yep.
You will see similar ratios versus the standard pneumatic nebulizer. That can typically be, depending upon the spray chamber system you have, of 0.5 to 1% cerium oxide, because even with the condenser in line, you will have water vapor that still goes out and gets into the ICP. To lower that further, you would need a membrane dissolvator. And that is available as a module that can be added to an ultrasonic nebulizer. And in that case, typically you will push cerium oxide to cerium ratios well below 0.1%, generally at 0.05% or lower.
Okay. Are there any plans to try heavy metals analysis of flowback water from oil fields using the U5000?
Yeah, that certainly would be a thing to look at, especially fracking water. That would certainly be a potential future application. That type of application has been run with our AS Express Plus system for rapid sample, but If there is a need for detecting lower levels, certainly that's something that can be looked at with the USN.
All right. Do you have information of uranium in South America?
No. You probably could certainly, of course, look online if there are geographical atlases that may show the prevalence of uranium in certain areas. In this case, we were looking at areas in Europe and then in the United States per the requests that came in.
Are you using internal standards with your system?
No, we did not in this case because we wanted to see just how good or how not good the data quality would be in this very hard water matrix. Certainly in practice, you would use an internal standard to compensate for changes in the sample matrix, perhaps using traditional internal standards such as scandium and yttrium.
All right. Do you have any more questions out there?
Again, okay.
Do you have ICP-MS data?
Or ICP, perhaps ICPMS data?
Sorry, ICPMS.
Yeah. The only ICPMS data we took here was with the standard nebulizer, just doing a check of the uranium and groundwater. Certainly, the ultrasonic nebulizer can be connected and has over the years to an ICPMS. Typically, then, you're looking more at elements above mass 80, things like rare earth elements and actinides, where you can push detection limits down very, very low. In that case, of course, it depends upon the cleanliness of your reagents and your laboratory vessels, everything to achieve very, very low levels. There was one particular application that I can mention was looking for very low levels of platinum group elements, particularly gold. Okay. But that has been done with the ultrasonic. Probably more so in past years before ICPMS became very much more sensitive in recent years. But,
interesting.
Oh, sorry, ICPMS. Yeah. Yeah. But certainly
when I read it, I was like, what's IDP?
You certainly, again, can easily interface the ultrasonic nebulizer to an ICPMS. Again, you simply are going to use the nebulizer gas from the host ICPMS to sweep the aerosol to the plasma.
All right. What is the factor upon comparing the standard nebulizer with ultrasonic?
The factor is simply that we compared actually two factors: raw sensitivity, and then we also compared the limits of quantitation after factoring in any noise from the background.
That was for ICPMS?
With the ultrasonic, that was for ICPMS?
Yeah.
Oh, okay, for factor for ICPMS.
You're just saying that it's for ICPMS.
For ICPMS. Again, it would be if you compared the standard nebulizer with the ultrasonic. So if you had a very clean matrix and an area of the ICP mass spectrum which is very clean, particularly at high mass, yeah, in general you might be able to see a factor of up to 10-fold improvement, again depending upon how low the blanks are. And that's going out into the area where you would have rare earth elements, platinum group elements, and actinides.
Okay. Do you see any memory effects by using Tygon rather than Teflon tubing for the sample line?
There can be if you're collecting more salts that may stick to the walls of the Tygon. Most of the memory you will see with the USN can come over time in the heated part of the J tube. If deposits do build up in there and they are part of the analyte mix you want to look at, that's something to always monitor. In the Tygon line, yes, it can occur. Typically, I recommend keeping the line as short as possible, and certainly you can move to Teflon or an FEP line Tygon, so things don't stick as readily.
Okay. Do you have any more questions? Okay. Well, we appreciate you joining our webinar today. Hopefully you'll have a great day. Thank you.
Thank you.